Welcome, everybody. You are in the technical track, the finance portion at the Global AI Conference, and if that's what you're looking for, you're in the right place. Want to welcome and introduce SK Reddy. SK is VP of Data and AI at Fidelity Investments. He has been a successful entrepreneur a couple times over, and he was also previously at Apple developing and innovating AI solutions, which became part of the iPhone and other Apple products. Welcome, SK.
Thanks. Thank you. Hello, everyone. Good morning. Thank you. You know, the worst time to speak in a conference is just before lunch. I know after this session, I think you may be breaking for lunch, but hopefully this session is going to be interesting. After the advent of fantastic deep neural networks in 2012 or 2015 in image processing, and of course, year 2018 has been extremely important for NLP, more and more people are realizing, or companies are realizing, that the data what they're getting is not necessarily balanced data. And when I say a balanced data, let's say just talk about the most simple situation of just two classes. And if you're trying to develop a machine learning model using a classical machine learning or deep learning models, and if you're trying to do, let's say, a classification. When I say classification, do remember that classification is a type of search, and a search is a type of recommendation in general, and recommendation is a type of a classification. So whatever I think you call it, and if you're trying to identify the class the sample belongs to, and you're developing a model, you want to have a balanced data, because I think the models that need to be developed, I think, has to look at both the positive class and the negative class so that they understand the intricate background in the data and then generalize based on the data. But in reality, I think you don't find that balanced data all the time, and that's because I think data collection is costly and sometimes it's not even available. But there are certain situations where you can't even get the balanced data because, let's say, in a traffic accident situations, or in a medical death situations, or any medical treatment going wrong, or intrusion detection in network, or could be any type of situation, fraud detection, in credit card fraud, warranty fraud sort of things. You don't find too many transactions which are the so-called positive class, in this case fraud or crash or similar classes. Even if you want to spend more money, you can't get the data. And in that case, how would you develop a model that actually understands not just the background or the intricate information about the majority class, but also about the minority class, so that the model is generalized enough to find out when it sees a new sample, whether the sample belongs to the positive class or the negative class. By the way, if you're looking at any model development in an imbalanced situation, the minority class is always called the positive class, and the majority class is always called the negative class, because you're looking for a model that can understand and look at the minority data set and understand how the minority data set works, and then generalize based on that. That's what it is. So I'm going to talk about, for the next 25 minutes, talk about some of the models and techniques available. Many of these techniques are very, very common sense. I think I just need to be aware of what these techniques are. Otherwise, implementing these techniques are extremely simple. Every time I talk in a conference, I want to put a disclaimer out. I'm not talking about my company I work for right now, but I think based on the wisdom I acquired, whatever little I acquired in the last so many years doing machine learning and AI, I'm going to talk about if you encounter a data set which is actually imbalanced, and if you're asked to develop a machine learning model, I'm going to talk about the techniques and the approaches. I would explain a few of the techniques, and towards the end, I also talk about some of the use cases. All of the data I'm using today is published information by organizations and research institutes. And at the end of each slide, I would actually show the link where I've got the data from. And before I even talk about imbalanced data, what exactly is imbalanced data? When you find a set of transactions, let's say a credit card transactions, you have millions and billions of positive transactions, which are good transactions, let's say positive, good transactions, and then you have a few fraud transactions. And I'm going to talk about only the simplistic scenario where the model is looking at two classes only. There are situations where you can build a model with imbalanced data for multiple classes, but here I'm going to drive home the point on how to build a model for just two classes. some of you in the audience, I think, may be comfortable with some of the terminology I'm going to be using. So I would try to balance between what you guys already know versus what you don't know. I would quickly touch upon some real fundamental information, fundamental details, but I fast move into some implementation examples, but you can always ask questions to find out. So just to drive home the point about what's the imbalanced data means, if you look at some of the pictures here I've got from internet, these are the reflections of a two-dimensional portrayal of a data set, and to show the difference between the majority and the minority. Here, it's not just the virtual count of the majority versus minority, but also you see the distribution of data. For example, let me look for my mouse, look at this. You have this majority class here, and then you have the minority class here, but here the class is completely overlapping. You can't have a very distinct delineation or a line or a boundary to show where the one class ends and the other class starts. I think that's a complicated situation. In this scenario, even though the minority class is kind of overlapping, but I think they seem to be really, really clustered in one location, I think it may be easier to do some sort of, let's say, support vector machines to draw a circle around it or some sort of a line border around it, but it's not all the time case. But look at this scenario here where you have distinct subclusters of information. So if you have a majority class and a minority class, but they are not contiguous, they're not distributed uniformly, and then it becomes more difficult for you. So before you start any of the machine learning model development for your imbalanced data, you want to actually have to visualize how the data looks like, because then I think you can apply the right technique and also write the sampling methodology. When I say sampling methodology, it means how do you balance the imbalanced data. Before we get into the details of how to balance and the techniques, the models which are going to be looking at the data and then generalizing on the models, or the classification models, there are a couple of types of metrics you want to be aware of. You might have heard of accuracy, you heard of precision, recall, and all of that stuff. The problem with accuracy in an imbalanced data set is the model understands the majority class so well and does not understand minority class as well that every time you run the model, it seems to be leaning towards the majority class, and hence you are not actually getting the benefit of learning from the minority class, and the model actually is failing. So the traditional metrics of accuracies and sometimes the recalls are not really useful, whereas the negative predictive value and positive predictive value are a couple of metrics which I think you want to focus on. It's called specificity and sort of kind of a little bit of precision too, and there are other metrics which will help you to figure out whether the model is actually learning fine or not. This is for classification. You find imbalanced data scenarios which you would be using to develop regression models too, but less popular. The most common metrics used in the regression techniques is mean squared error or MAD, the mean absolute deviation, but those are not, again, absolutely useful when you're doing an imbalanced data. Area over the curve is one, regression error characteristics is another one. I think I've seen a lot of people using ROC. The ROC space for regression is another metric which you want to use. So when you develop a model and when you test the model or validate the model, you want to go back and make sure it complies with these metrics expectations. As I mentioned earlier, I do have the links at the bottom of each slide. If you want more information, you can get that information from those links. There are a few simple sampling techniques, and there are a few advanced techniques to sample the data to make it balanced. And I wanted to talk a few of these, but not all. The basic sampling, if you have a majority class and a minority class, look at the picture here, you have this majority class and the minority class, you can do something called oversampling. You can just add more of the same of the minority to bring the minority class the same size of as the majority class and then do it. Or you can, so here you're talking about oversampling where you're actually adding the minority samples more and more. And you also have the opposite of undersampling where you can look at the majority class and take out a few, so pick a few of the samples and see you can bring the balanced data. That's the most common technique that's been applied for a long time, but that's that's not the best technique. And again, in the undersampling and oversampling, you actually can have a random undersampling. You can just pick any samples you want to pick and then eliminate them. Or there's something called focused undersampling or focused oversampling, where you want to design a few criteria of what type of samples you want to keep or what type of samples you want to throw away. So if you're talking about just a random undersampling or oversampling, you can also use a combination of this, where instead of using just only oversampling or only undersampling, you can do a combination to bring it to certain size. Even though this seems to be the easiest and most commonly used, or has been used for quite some time, they're not the most ideal models, because in you're doing the random or sometimes even focused undersampling or oversampling, you may be eliminating some of the critical samples, especially in the minority class. If there are very few, let's say it's only 1% or 2% or 5% of the data set is minority class, and if you're eliminating part of that, then you're depriving the model of looking at some other extremely good samples. But also, not all samples are exactly the same. Not all samples are of the same weightage. Some samples actually carry more information about how to generalize, and the model has to look at those samples, and random undersampling or random oversampling would actually cloud the understanding of the model if you do just random. So obviously, if you have a slide called basic, there must be something called advanced. A long time ago, when I was about to speak in a conference, and I asked an expert, how do I make sure I do a fantastic presentation? Then he said, first of all, prepare well, and then understand who your audience is. And the third one, he said, once in a while, crack some jokes and see if people, I think, are getting your jokes, and if they're not, that means not paying attention. So if I have a basic slide, there must be an advanced slide too. Oh, still not working fine. Okay, fine, never mind. I'll go on, maybe I'll talk about more slides. I think maybe this is the before lunch session possibility. Okay, among the advanced techniques, there are a few undersampling techniques where you look at the majority class and take a few off. Tomic link or T-links is one technique where you would eliminate samples from the majority class which are close to the border between the majority class and the minority class. Because a sample which is deep inside a majority class or deep inside a minority class, they are in a safe zone, and model can completely understand what the sample is trying to communicate when the model is trying to generalize. But if something is very close to the border, depending upon the thresholds you decide for the classification threshold, sometimes the model may assign a sample a label, positive or negative, just because of the threshold limits. So in other words, any sample that falls at the border of two classes would be predominantly noise or less valuable than the samples which are in the safer zone, which are deep inside the samples, deep inside the classes. Tomic links or T-links is a technique where pick any sample from a majority class and a minority class. If you find another sample whose distance between the third sample and the minority sample and the distance between the third sample and the majority sample, if there is one such sample, eliminate the first two and focus on the first and the third. And if there is no sample that is closer to this minority and the majority sample, which are so close to each other, that means they are very close to the border of these two classes, and they are contributing to the noise. any sample which is so close to the border will contribute to the noise, and to eliminate it. So here, if you look at, these are the T-links. You actually see one sample from majority class, one sample from the minority, and they're so close to each other. Even if you do a supervector mesh or some other model here, the demarcating line would actually be so confusing, and these samples which are so close to each other is difficult for the model to understand, and then eventually when you start inferring using the model, you will not make a good sense. So you want to eliminate this. So what happens, this is the data set which you see lots of samples, there's a lot of overlap here, and then you run the T-link technique and identify what those T-link are, and then you remove the majority class samples from there. So now you see a little bit of undersampling happening. Some of the samples have been taken out. Also, you see a clearer demarcation line or class boundary between the majority class and the minority class. That's T-link. Now, T-link can also be applied sometimes if you have lots and lots of data on the minority class. You can also apply it there, because any sample, as I mentioned earlier, whether it's a majority or minority, if it's close to the border, it's just adding to the noise. So you don't want to do that. But I mentioned earlier, in a minority class, if anyway you have less number of samples, maybe you want to keep minority class and eliminate the majority. So one-sided selection is you apply T-links or any other identification technique to eliminate samples from the majority class. And the neighborhood clustering clearing rule is sometimes you find outliers, and you can figure out by looking at the visualization of the data, you can identify, again, using T-links or other techniques. There's another technique I'm going to talk about in the next slide. You can use that to eliminate the outliers and unrepresentative data. When I say unrepresentative data, imagine a big, massive blob or a cluster of majority class, and you have the minority class, maybe let's say concentrated but overlapping in one side, but you may find small subclusters of minority class distributed across, and that subset or subcluster is so small, there's a very high possibility that that data is not representative of the minority class. And those are the unrepresentative data. You can eliminate those too. SMORT, minority oversampling techniques, is where you're trying to focus on how do I add more of the data. SMORT is the most commonly applied techniques. I think any of the programming tools, machine learning tools you may be using, you may have an API call already right there to help you do it. SMORT is you identify a sample from minority class, identify k nearest neighbors in the minority class, and then when you draw a line, connecting line between the sample and the neighborhood samples, you can add synthetic samples between these two samples on the line connecting them. It's like this. You see, let's say you pick this sample, and if your k is 3, the 3 nearest neighbor samples are these. And if you want to, let's say, twice, or if n times, if you want to increase your minority class, n is equal to, in this case, 2, you add 2 more synthetic data points on the line connecting between the primary sample and the neighborhood samples. Now, n can be any number if you want to triple or increase the magnitude. SMORT is that very, very simple technique. Pick any minority sample, identify k nearest neighbor in the minority sample, and then depending upon how many times you want to increase the minority class, you add the synthetic examples there. And here you add synthetic examples by just doing basic perturbations. Let's say you have a customer data of customers of variety of age. You can add between 2 samples the synthetic data where the rest of the information remaining same. Maybe you can change the age of the customer, or let's say any other important feature, and then you create a synthetic data. In the last 10, 15 years, I think there were lots of additions to SMORT have come. There are lots of stuff listed here. So if you have some of the data is a continuous data, some is a discrete value, how would you do that? There are different techniques for both SMOT for nominal and continuous. And then you also have a local neighborhood SMOT. Local neighborhood SMOT, it looks at if the data set is distributed, minority class is distributed in multiple subclusters, you can focus on those clusters which are actually smaller than the other minority subclusters, and then maybe you can increase the size. Like here is an example of, you see a minority class distributed a little bit here and a little bit here, and maybe I think very, very little here. If you feel this is a representative area for your minority class, you can run a SMOT, the local neighborhood SMOT, to increase the data. This is how it looks like after you have. And there are similar techniques as SMOT 1 and 2, where you can add more of the SMOTs and depending upon where the data, the minority class is. And you also have clustering-based oversampling, where if you actually visualize the data into a cluster and pick any minority sample, identify the nearest centroid of one of the minority clusters, and then add the synthetic data in the process. Those are some of the SMOT or variations of SMOT data, and there's lots of more information available in these papers published. These are as old as 2016 to as recent as 2019, June. But there are a lot of other techniques, variations have come in too. I've not captured all of them here. Some more, it's called edited neighborhood, nearest neighbor rule. I mentioned earlier, SMOT basically talks about k nearest neighbors and then pick any of those k nearest neighbors. But edited nearest neighbors are if any of those neighbors are too close to a majority class, or in this case, whose class differs from majority class of at least 2 of the 3 nearest neighbors. That's an edited nearest neighbor. I've seen people using SMOT plus ENN combination. Condensed nearest neighbor class technique is a very similar one, where if you take one nearest neighbor as a method to identify whether the sample is really belong to the right class or not, you can take subsamples of the majority class and the minority class, run a model and see if the model is doing fine. Then you feel the model is learning from that subcluster of the minority and the majority class, and then you can add more samples for the minority class in that sense. There are a couple of other techniques too. I have another, I think, 12 minutes. And I'm not touching intentionally the deep learning methods about some other data imbalance. Both natural language processing and image processing, I think, are really full of data sets which don't have balanced data sets. But I won't talk about that here. Here is a paper that published to compare just a few of the techniques. For example, the basic SMOT and ENN combination, and there's a technique called adaptive synthetic, ADASYN, and then CBOS, clustering-based oversampling. They looked at a bunch of data. It doesn't matter what data this is. All of this data is imbalanced data, and if you look into just using the plain imbalanced data and run a model, what are the precisions, recalls, accuracies, and F-scores, and G-mean scores. And once you apply any of these techniques, the imbalance adjustment techniques, how the precision, recall, accuracy numbers change. So this is one of the proofs, or many papers available, to show that using an imbalanced data as is may not work all the time. I remember, I think, a long time ago when I was working for a very popular tech company, there was a fraud detection model I think we were working on, because this company was selling lots and lots of products online, and the company wants to look at the fraud transactions, both the credit card fraud and warranty fraud. There was not enough data about the real fraud, the minority class, the fraud data. We ran the we thought of developing a model called one-class SVM or one-class classification, where you don't need to really focus on the minority class, just focus on the majority alone, or just focus on the majority alone, a minority alone and not the majority, and develop a model. That worked for a while, but I think in the long term, I think you want to have a model that looks at both the majority class and the minority class. So one-class SVM, I think, still works, especially if it's a non-business critical project. Let's say if there's no life and death situation, there's no revenue impacting situation, I guess you can still use one-class SVMs. This is an ensemble of SVMs where you can, there's another publication that I saw recently, where if you have a majority class here and a minority class, you have an ensemble of undersampled SVM. So you take the minority class all the time, but you take a bunch of majority class, subcluster of majority class, and in a random fashion, and do an SVM models, but instead of taking one SVM model, take an average. So have an ensemble of SVMs and then take an average of it. And ensemble as a technique or approach has been quite popular for so many years in machine learning, especially in classical machine learning. I think as an ensemble is an approach a lot of companies prefer to, instead of just using one single model. I'll talk about a few use cases. Here I'm not going to be explaining how the model was developed on this data, but I want to highlight 3 or 4 different scenarios in a credit card transaction or a traffic situation or a network situation or any such financial services maybe, how you would develop or what type of techniques you work on your minority data to just bring it to a certain balance level and then apply techniques. Here is one, for example, imbalanced credit card data. If you look into the distribution, the minority class is 6%, and then you have the rest of the thing is 94%. You see, you have the class label is service delinquency in 2 years. That's a binary value, yes or no, 1 or 0. But the interesting is the rest of the data, a good amount of the data, is an interval. It's not actually a discrete value, but it's always an interval. And that becomes a little difficult to model. So you actually have 4 models here. Model 1, the logistic regression with just the basic data provided. But you have this model 4, which actually talks about using a logistic regression with discretized form of variables. So you actually, even though the variables, the features are continuous, you discretize it, make it do a couple of buckets, and then run a model. And actually, the model seems to be performing better in this case using that data balancing techniques. Here is a fantastic paper on comparing some of these techniques across lots and lots of data sets. I think they applied on 53 different types of data sets. I got only, these are the 53 data sets, and if you look into the data distribution, you find the majority class. This is the total data set, and this is just the minority class. And if you look into the size, the absolute size of the data set, you can run or develop a model with very, very small data sets. Of course, just three samples in a minority class, I think it's a little difficult. I've not read the complete paper for that, but I think if you have, let's say, 20, 30, or 50, or 60, you would be able to make a decent model out of it. And this is what I think this paper talks about, how if this is the original data set, you can run, since data is completely missing at random of 50%, and then 50 missing at random at 90%, you try to create you can reduce the majority class or increase the minority class and run models. And this is one single paper if you want to look at to compare and contrast between various data sets, and these are, the font is too small by design. I couldn't fit it in. The same professor who told me how to give a presentation, he told me, don't have your slides too cluttered, and I forgot today. In a Medicare situation where you always have data which is imbalanced, and especially the covariates about the patient, I think they change all the time, but you want to find out how the effect of individual treatment plan is impacting the individual or the patient. Here is a paper which talks about the variation or the maturity of the model to understand the type S error. Type S stands for sign, which is also like positive class or the negative class. The type S can be positive S or the negative sign or the positive sign. This is a patient-related information where they applied some basic data expansion techniques using SMORT, and the model actually came out well. Traffic accidents, again, you don't find too many traffic accidents. If you are looking for an ideal data set, you want more and more accidents to happen. Well, that's not the right thing to expect. Anyway, so here are some basic models using least square principal component analysis, and you also have probabilistic PCA, sorry, typo, and variational Bayesian PCA, probabilistic principal component analysis. And the accuracy of the model actually is really, really high based on some of these techniques. So even in the situations like a traffic accident where the data is really small in size, but also the type of traffic accidents are so many, so varieties of traffic accidents, and some of the causes, the drivers, or the features also are so different. Cyber attacks, if you have things like denial of services, malware, attack-on, you have the defacement and MEU, the malicious emails and malicious URLs. If you run basic model here, I think the technique was SMORT++. The SMORT++ is nothing else but certain percentage of the majority instances that are very close to the minority class are eliminated. And here in this paper too, you find the models are really understanding better based on the balanced data set which you arrived at by using techniques. Another data set, again, the reason I picked up this is that the size of the data set is very, very small. Here we're talking about recommendation engines. And if you have, here is the percentages of imbalance. You have 0.3% imbalance here, and in some data sets you actually have 70% imbalance in majority class. And still, if you run a model like SVM using some of the basic data balancing techniques, the models are actually performing better. By the way, after talking about all the necessity to balance data, balanced data set is not going to guarantee you a good model. So here's a paper which actually proves that. Even you look at some of the data set here, you have a huge imbalance. You have only the minority class happens to be 4%, but there are some data sets which are almost close to 50%. You actually have data sets which are very, very balanced, but still, if you look into some of the PPV values and NPP values, and they're really unpredictable. So the models, so balanced data set is required, but that's not a sufficient condition for the model to be really intelligent enough to figure out. That was my last slide. Presentation is over. Thank you. Thank you. If you have any questions, I'll be more than happy to take. I think I have another 5 minutes for the next speaker to come in. Yes, sir.
I have a very basic question. What can be balanced data versus balanced data? To me, it means homogeneity with respect to some criteria. If homogeneity is there, you call it balanced.
Yeah.
If not there, you call it imbalanced.
Absolutely. That's a very good question.
It's true that imbalanced data is like information research. But can you respond to that? What exactly, if you take a domain of knowledge, what do you call imbalanced data? What do you call balanced?
Yeah. I don't think anyone knows the absolute answer for that question, because initially when people said balanced data, I think just numerically balancing the number, just the samples. If you have a million samples of majority and then let's say just 100 samples of the minority, then you want to actually have either the majority also come down to 100 or minority go up to 1 million or somewhere in between. So it was numeric was the definition earlier, but I think now, like you rightly pointed out, when you say balanced data, it has to, the samples have to be reflective enough of the general underlying causes or the drivers that's making these samples appear. And you can't define by just looking at the random data or just with the naked eye. You can look at model when it sees the data and starts assimilating the data, then it knows whether it's finding the right balanced data or not. And hence, I said earlier too, the last slide, even if you have numerically balanced data, the model still won't understand because the synthetic data you got, or even the real data you got, but it was such a bad data you got, even though it's numerically balanced, it's not reflective of the real world scenarios the model is going to look at, and hence it's not balanced. So it has to be, so the generic answer to your question is, it has to be, the balanced nature has to be that all the samples have to have some reflection of the wisdom the samples want to bring for the model to learn, so that the model can generalize enough. And that can be never the truth, because if, going back to the traffic accident situation, you never know what type of accident that's going to happen today. Maybe I think you can have even just two automobiles crashing into each other, but there could be something else. Maybe once you have other types of automobiles coming in, people coming in, or so the model can never know exactly what the future sample is going to be. So that's what I can say.
So there is an underlying set of criteria that's being assumed, calling something balanced and balanced.
Yes, that's true. That's true. So the definition of balance, I think people have to be really careful. That's why my last slide is, just because numerical is balanced, I think it's not sufficient. And even if the undersampling techniques or the oversampling techniques I talked about, I think there's lots more research going on how do I undersample or oversample only those which really make sense. And when you say, what do you mean by really make sense? Then the question is, those samples have to be reflective of the general understanding of the real world you're trying to model into. And I remember, I think 20 years ago, there was a famous statement. It's called Box's rule. All models are wrong, some are useful. So when you generalize anything, any data set into a model, that's not the real world, but I think that's a comparably tolerable model which reflects the world.
So when we are doing the oversampling, do we have any parameter into the oversampling techniques which will put constraints so that the decision boundaries are not deteriorating by the additional samples, but only we are adding oversampling, we are doing the oversampling only at those places where it is going to help the decision boundary get better?
Yeah. The oversampling, when you say boundaries between two classes, the most simple assumption is you can imagine, okay, the two samples are so distinctly placed if you visualize them in a two-dimensional space, but that's never the reality. You actually have not just overlapping the classes, but you find minor clusters happening, and sometimes the outliers may not capture the real essence of the minority class, but sometimes the subclusters that form of the minority class itself may capture, some subclusters may capture better essence of the minority class compared to certain other, and you just don't know unless you start doing the modeling. So it's more of a hidden trial sometimes. You actually can use the techniques, build the model, see how the model is responding, and then go back and apply different techniques. That's the reason why just in the SMOT alone, the minority undersampling, synthetic minority undersampling technique, there's so many additions that have come in, because you can oversample the minority, but then way to oversample, which sample to oversample, and also what type of perturbations you can create, or by creating additional subsamples, you're not moving away far from the reality, because you want to create the data set, the synthetic data set, which is more close to the reality. And that's, I think, is not an absolute science. I think it's still in a hidden trial method right now. That's the reason why you find SMOT itself has gone through SMOT++ and SMOT ELC and all of this stuff, plus other techniques have been combined with SMOT with CBOS and SMOT with ENN, SMOT with CNN, all of these things are being done. And I'm only talking about just the classical machine learning, but if you get into other deep learning methodology, there's so many other techniques for oversampling. But at the end of the day, I think you want to find the data which actually is reflective, and you create new data, which I think we have not figured out how to do it. Yes, sir.
So I think your last slide really highlighted difficulty with how far you want to go with the imbalanced sample. My question is, does how far you go depend on the type of problem you're really solving? The same data set could actually be answering different questions, and the different questions actually require different degree of balancing of the data. And to extend that, if that is true, do you think there is potential to use machine learning techniques to figure out, depending on what type of problem you want to do, and then you can choose how far you want to go?
Yeah. How far you want to go is actually a very good phrase. I think that's what I think every company is struggling with. How long can I wait to develop the best model? How much money I can spend? How much of data I can get? These are all some of the factors. Sometimes there are other factors which are also governing. The cost of making an error. For example, if it's a delicate life and death situation or extremely revenue impacting situation, the cost of making an error is so high, you want to find out the minority class is really reflective of the scenarios is. So, good number of use cases where you have imbalanced data, and if that's very critical, how far you want to go, human in the loop has been an absolute requirement. Even, in other words, I think when you have a model which is making a prediction, and still many times that's called active learning. When you have a model that comes in and makes a prediction, or while training a model, you actually have a human in the loop. Like in a Medicare situation or a financial services, the doctors and the experts come in and give a feedback to the model to make it understand better. So how far you want to go? Yeah, there's so many factors which companies want to get into.
That's great. Thank you so much.
Thank you. Thank you very much. Yeah, thank you.